I'm Ben Newman. I'm working at Willapa National Wildlife Refuge Complex and Malheur National Wildlife Refuge. Sorry, 1 sec. There's a dog
talking about wildlife
in the background.
Good joke.
And yeah, so I saw that some of your work was related to climate change impacts in the high desert. And so I think that the workout that I'm doing out in Malheur is definitely pretty relevant to that. I'm looking at climate change impacts in the high desert and helping them trying to look at how much water they currently have on the refuge, and then looking at under different climate change scenarios, how that water, like the amount of water that they currently have could decrease, or to what extent it'll decrease, and how the different water sources that they have will change. And yeah, for my work at Willapa, I'm mostly looking at sea level rise right now. So probably a little less relevant to what you're doing, but.
All right, thanks. Gabriel, would you mind doing an introduction?
Hello. So you caught me snacking. My name is Gabriel. I'm based out of Big Oaks and Muscatatuck National Wildlife Refuge Complex. I'm based in southeastern Indiana. I've been to a couple of the webinars with that you were hosting, and those were super useful. So I'm excited for today, and just to learn more about climate models and climate predictions. And do you also, Scott, want us to just describe the program? Because I know it sounded like just a bit.
Thanks, yeah.
Yeah, like a
maybe.
brief introductions. The other fellows can fill in what I miss, but we are a 6-fellow cohort called the Civilian Climate Corps Fellowship, and we're based all over the United States, continuous, and Alaska. So we have all in the 6 different refuges. Well, 7 refuges, I guess, because Ben is in 2. And we are planning to utilize the RAD framework and the Resist Accept Direct framework in this project workflow that involves 4 phases. We're currently on the 2nd one, which involves utilizing or running climate change vulnerability assessments to just pretty much assess the most vulnerable habitats and species in each refuge, to then see if any ecological transformations are expected to happen or currently happening in our refuge, and then use all that information that we gather, all that research that we gather in that data to give management recommendations to our refuge staff. And those management recommendations are supposed to be framed around RAD and regard, climate change adaptation. Both, and the recommendations are going to be for like habitat management, but also for infrastructure management. That's something we're going to focus later on. And sorry if I missed anything. Try to condense it into just a few words, but yeah, that's what we're doing.
Excellent. Thanks, Gabe. And Dina, would you mind going?
Okay, so I got my microphone to work, except not my camera, but I'll work on that.
Yeah, no
Okay, so I'm Dina Martinez, originally from Colorado, but have recently moved up to Fairbanks, Alaska, and be working with Yukon Flats National Wildlife Refuge. I will be working with Don Magnus to look at the boreal forest up here and do an ArcGIS project focusing on that, hopefully to broaden that to other refuges that also deal with boreal forests.
Right, yeah, I know Dawn and on a project with her.
Excellent. Let's see here, Daniel.
Hi, I'm Daniel. I'm from Tampa, Florida. Currently, I'm in Santee, South Carolina, in the Santee National Wildlife Refuge, and we'll be doing exactly the same thing Gabe kind of laid out as far as looking at the most important climate drivers and what our most important resources of concerns are going to be here in this refuge, and then trying to determine whether the high heat days or heavy precipitation events or those stronger storm events like hurricanes, if those are going to have the effects of creating those ecological transformations and what we can do about it. Separately, though, I think we are also informing the framework process overall to see what we can help in shoring up the process and making sure that it is as fruitful as it can be. As far as being able to apply it here to Santee, mostly what I'm looking at is the wetlands like our Carolina bays, our managed soil impoundments, or the longleaf pine stands as well that we have here. So there's a lot of different types of considerations to look at.
Super.
Thank you.
All right, Daniel. Let's hear Ashley.
Hello. Hi, so I'm Ashley Garcia. I'm originally from South Texas, a small little town, but I'm here at Aransas National Wildlife Refuge. And so same thing as all of the other fellows. Gabriel, I think he explained our program really well. I'm going to be looking at mainly sea level rise, migration of marsh, and we actually, Gina Moon, which is one of the zone biologists, she recently, I think either a day ago or 2 days ago, sent out the surface elevation tables for the Texas Gulf Coast, and it's looking at that marsh migration. And unfortunately, we're gonna kind of be seeing, some migration of those marshes, and so that's one of the things that I'm gonna be looking at and implementing into this program, into our fellowship here. Sea level rise as well as drought. We may be experiencing some more drought events throughout the years and long term. We're actually kind of in one right now. So we haven't really seen that much rain here recently. But yeah.
Thanks, Ashley. So the final person is Lane Lopez. He's based out of Bosque del Apache in New Mexico. He's probably out moving boards around and working on some water management out there as we speak. I would imagine he gets pretty active in some of the actual management activities that are happening on the refuge. So it isn't able to make it today. But we have those six fellows that are kind of spread across the U.S. and each one of them has a mentor. And so I'd like to, for the mentors, if you wouldn't mind, to introduce. And I've got Jimmy, since you've got your camera on, would you mind doing a quick introduction too?
Yeah. Good afternoon. Good morning from Fairbanks, Alaska. Jimmy Fox. Gender pronouns he, him, his. Sitting here on Trothyeta, the traditional lands of the Dene people. And I don't consider myself Dina's mentor. I'm learning from her too. Don Magnus is the real mentor, but I am the refuge manager, the host station for Dina. So I've tried to make sure that she has chest waders and I'm there with a credit card and some protection, direction, and order when she needs that from me. Happy to be here.
Excellent. Thanks, Jimmy. And you can be my mentor anytime, especially if you got a credit card. Yeah, man. Hey, Jeff, Mr. Mackey, would you mind doing an introduction?
Sure. Yeah. Scott, before you can use a credit card, you have to have money in the bank to spend, and we have none. Good afternoon, everyone. I'm Jeff Mackey. I'm the project leader, refuge manager for the Malheur National Wildlife Refuge. Been in the high desert most of my career and been in desert ecosystems my entire career, which spans about 37 years in the refuge system.
Excellent. Joe Sains, I've got you up.
Good afternoon, everybody. Joe Sines, I'm the refuge manager at Aransas here on the Texas coast, working with Ashley on the work that she's doing. So, nice to meet you.
Dr. Rob, are you around?
Yeah, I'm Joe. I'm at Big Oaks, Muscatatuck National Wildlife Refuge in southeastern Indiana.
Thanks, Joe. Let's see here. Who am I missing? Oh, Josh, would you mind doing an introduction too?
Hey, I'm Josh Booker. I'm a zone biologist in our inventory monitoring program in Region 3 with the Midwest. So I give support to Joe, Rob, and Big Oaks and Muscatatuck, and working with Gabe to incorporate climate change into the habitat management plan we're working on.
Thanks, Josh. Naomi.
Yeah, hey, how you doing? Whoa, Zoom has a close camera. Hi, I'm Naomi Fireman. I'm a past fellow. Actually, I worked in the Transportation Fellows program, which is a different program, but has very similar, sort of frameworks. So I'm here to kind of help out whenever I can, and I'm very interested in the presentation today. Thanks.
And last, Jaron.
Hey everybody, yes, I'm Jaron Ming. I'm the branch chief for Air and Water Resources, and have just kind of been helping to make sure the fellows have everything they need, and it's a job because they pretty much handle everything themselves, very self-sufficient. But it's been a great group, and appreciate Scott for organizing this and facilitating the discussion. Thanks.
Oh, I can't take it today. This one was all NIFR. But I want to now I think you at least you Imtiaz, you have an idea of kind of the scope of what folks are working on and the geographic distribution, and everybody is extremely interested in your presentation today. So I don't want to take any more time, but I want to turn it over to you and allow you to take it away.
Thanks, Scott. And yeah, I really appreciate everybody introducing themselves, and gives me a sense of what you all are doing. I must say that a lot of my climate application work has been with the Fish and Wildlife Service and has been very fruitful, kind of thinking about how to do actionable science with practitioners. So although when it comes to geography, I was really struggling with where all those refuges were located, so I need to do some work on that. I see that they're all over the place, and it's just difficult to know each. But I need to go to these places, I guess, to know them as I know the Park Service lands. So I'm Imtiaz Rangwala. I'm a climate researcher based at University of Colorado Boulder. It's the traditional lands of Arapaho, Cheyenne, and Ute people, among others. So, I just felt listening to you that there's a lot of application work already happening, climate science application and data application, and folks are already working with scenarios, etc. So it'll make my work easy as I do this presentation to go through this quickly. I have put, concepts and, kind of some information on kind of the nature of practice and philosophy of applying climate science, and then get into a little bit on, how do we do impact assessment and what are we thinking currently to do a robust assessment of climate change and incorporating the climate change uncertainty into understanding impacts. But there's a lot of uncertainty when you start to bring together the climate and the ecology piece that I'll show later. And then how do you make decisions, even if you have some robust information. So hopefully I'll try to cover some of that, and I'm really hoping that we'll have 20 minutes or so to kind of have some discussion. I'll share my screen at this point. And I am recording this this session, so if you ever need that. And I'll share that, Scott, the link, so you have this with you. I also meant to, I'm sorry, I'll just come out of this. I'll share this link with you, so you can just go through the slides during the presentation. Yeah, anybody should be able to view this. And Scott, please feel free to, I won't be checking the chat, but feel free to stop me whenever appropriate if there's a comment or discussion going on. So yeah, and anybody else too, feel free to chime in at any point during my presentation.
I'll try to keep track of those, the comments or any questions in the chat.
Yeah, great. Yeah, that'll be great, Scott, if you can do that. Thanks. Okay, so I thought start with some very basic concepts, and nothing more basic than talking about our climate system, a wonderful thing out there. But really what I want to say that our climate system is usually bigger than what we think it is. So simplistically, it composes of, and when we look at components, there's the land, there's the ocean, there's the atmosphere, and the interaction within these components that forms, some of the basis of our climate processes. But then, of course, we need to think about things external to this climate system that is very important to whatever goes internal to our climate system. And so much of our energy comes from the sun. In fact, 99.9% of energy that drives our climate comes from the sun. So very important to consider that external element, and any variation in that affects our climate. We are in a constant energy flux with the space. So you change anything there, it affects our climate system, and something we are doing currently to that in a very profound ways. Volcanoes, when they're up, they actually cause very significant climate transition on short-term scales, like a matter of years. You can have very severe climatic changes. So 1815, very big eruption. The year without summer, if you remember, authors wrote Frankenstein, etc. It's just so they can play a very powerful role. And in the future, we just don't know how volcanoes may play a role in coming decades, and affect climate trajectories, something we don't talk about much. So those are also external to our climate system. Anytime a volcanic eruption happens. Another thing that's external is what humans are doing in terms of affecting atmospheric chemistry. By burning these fossil fuels that are external to our climate system, you bring them very rapidly into our climate system, and that's affecting our climate. And and I really want to define what's happening. Think of climate change and how we define it. The main theme, for me, the main theme is the rapid heating for our climate system. You're just putting enormous amount of energy into this climate system in a very short amount of time. And so you can quantify in terms of, how many atomic bombs worth of heat we have added to our climate system. And that's about 5 billion of those since 1970. Or, in 2021, we just saw actually a shift in that. We're actually accelerating the amount of heat we're adding. And so you might have seen these headlines where we're at, in 2021, we added, 7 Hiroshima bombs per second of energy into our climate system. And much of that energy is actually going into our ocean, and some into other components. And again, this energy drives our climate and the changes in our climate. And especially we see it through the expression of climate extremes. But here really we are, so that background is really important to just appreciate the amount of heat we're adding to the system, and it really changes the response of the system. And it should be humbling in terms of, what these shifts could look like. And as we talk about, some of these numbers like changes in temperature, etc., And hopefully you'll bring in some of those numbers in our discussion later today as you're looking at these extremes and what you're finding. Yeah, it's really kind of pushed by that energy that we're adding to our climate system. So it's added globally, but then we're really looking at what is the regional scale response. And everything I talked about from here on is really looking at regional scale. The whole philosophy is looking at regional scale. And there's more noise at regional scale, of course, because the climate system has that stochasticity element to it. So what I'm showing you here are, some ways that you might have seen or displayed future climate projections in your studies. And you can just show a time series plot like this one of temperature. And I think the point to note here is that there's a spread in these projections. So there's a trend and there's a spread around that trend. So for example, this is looking at this county in Southwest Colorado. I'm looking at two different emission scenarios. The red is RCP 8.5 and the blue is 4.5. I guess you all know that, the medium and the high emission scenario. And again, you kind of see that if you really focus on these numbers, they're saying, at any point of time, let's look at 2100, that the temperature could be anywhere from 2.5 degrees Fahrenheit change to over 16 or 15 degrees change. And that's enormous amount of uncertainty if you really want to work with those numbers and make decisions. Same thing with precip, although if you look at the mean, the directional change is much more limited, but across the different projections, there's a variation of from minus 40% change in precipitation to over 40% change, plus 40% change increases. Or you can look at in this kind of scatter plot manner of just looking at what the future projection look like, and you kind of see the spread of these projections. And so this is usually what we call climate uncertainty, and how do we work with that climate uncertainty is the question that really bogs the practitioner, or has been bogging the practitioner in the past, and I think they're doing much better in the present. So what I'll do now is talk about the three sources of uncertainty that kind of drives the spread in the projections. And I also want to say the word uncertainty could sometimes be misleading. Uncertainty sometimes could be construed as something we just don't know and could improve upon. But here, most of the uncertainty I'm talking about is largely irreducible. And it's coming from certain, and we have seen that at least we have not been able to reduce that for the last several decades and don't expect to reduce it in several coming decades. But we can make choices, we can hedge and all, and reduce the spread to work with. So it all depends on the choices we make in terms of what kind of the spread of future climate projections we want to work with. So the three sources are changes in future greenhouse gas emission scenarios, differences across climate models and climate variability. And I'll go through these in a bit and fairly quickly, but I'll go through these in some detail. So starting with the emission scenarios uncertainty. So again, if you look at all the possible scenarios that as a scientific community we have created, they look pretty overwhelming to consider. And so especially by the end of the century, where those different trajectories of emissions could lead us, anywhere from stringent methods to curb down emissions to where we are maybe currently heading to these worst case scenarios that we may get into. And in one of the slides, I'll talk about some likelihood that we are trying to assign to these scenarios going forward. But the point I wanted to make for the practitioner's purpose is that the scenarios have a certain impact depending on the variables you're looking at and the time horizon you're looking at. So the choice of scenarios may not really matter by mid-century, but they do try to diverge. Again, here I'm showing the intermediate 4.5 emission scenario and the high 8.5 emission scenario. And I could have added other scenarios as well, but you'll see that they don't diverge in over the next 20 to 30 years. But after 2050, that's when they start to diverge. So if your time horizon of planning or decision making, or even doing your impact assessment is mid-century, then the choice of scenario do not matter much, and you can work with one or the other scenario. And I'll talk about more recent projects for working with this more RCP 4.5 type of scenarios. When you look at precipitation, actually here you don't see any difference between the blue and the red at all. So, and I'll show you some more examples of that. But essentially, emission scenarios have very limited effect on precipitation change. That's amount of what precipitation that can come in your region. It of course may have a very different effect on extreme precipitation behavior. So how the flood risk and all that could emerge out of a high emission scenario with a much greater warming than a lower emission scenario with a kind of a lesser amount of warming. So here I'm just talking about the total amount of water that will come into your system, and not how extreme behavior of precipitation may shape up. Yeah, I think somebody raised a hand. Go for it.
Yeah, just on that projection for precipitation, is that factoring in evaporation? So, is there not going to be a water deficit, or maybe?
No, it's not factoring in evaporation at all. So for that, we should look at something like soil moisture, which factors that in. So this is just pure precip. So what you're seeing is a slight, in this, like at the mean, you basically seeing a few percentage increase in precipitation. And that's also is shown maybe in one of those. I'll show another plot about it, but maybe you can see here, slightly different region, that there is a net increase in the precipitation. We look at the mean change, but then the spread is pretty huge. Does that answer?
Yes, thanks.
So here's another way to just tell the same thing, where I'm showing you, and I'll show a lot of these scatter plots, so maybe I should spend some time on this. I'm also keeping an eye on time. I don't want to take too much time just presenting my stuff. So here, and we're using a lot of these, what we call bivariate scatter plot to look at uncertainty and also work with what we call in climate scenarios. And if you've read our paper, this figure from that, we talk about that a little more. And more we're finding other practitioners that are using this approach, like the Park Service, among others. And tools are being developed. And I'll show a couple of tools that you can use to kind of generate these bivariate plots. But I used to do these for like over 10 years now, and just to kind of help me think through the uncertainty and how to work with scenarios. And what I'm showing here is temperature. This is again for a region in Southwest Colorado, and looking at like 35 models, 2 emission scenarios, and changes in temperature and precipitation. And the point I want to make here is, by a 2035 time horizon, there's very little difference between the red and the blue dots and the spread across both temperature and precip. It starts to change by 2050, and this 2050 is basically a 30-year period where 2050 would go, consider time period beyond 15 years. After 2050, 2050 years, 15 years before 2050. And so you start to see the red and the blue kind of start diverging across temperature scale, but not so much across precip. And by 2070, the overlap is hardly there between the red and the blue dots. So in terms of warming, the two scenarios are very different. But if you look at the spread across the x-axis across precipitation, it's really the overlaps is substantial. In fact, there's no difference across the two, no significant difference. So again, the same point that emission scenarios have influence on the temperature and everything that temperature kind of forces, or the heat element, or less on, how much change in precipitation happened. And just want to make the point, and I want to make that point again, that the reason for that, we feel that a lot of the variation in the precipitation seems to be driven by just the variability, the stochasticity in the climate system. I'll talk about it a little more. So I didn't mention that, there's an effort in the last couple of years to assign likelihoods. And so we've been staying away from assigning likelihoods to different things as a climate community. And I think it's changing a little bit. And, we are pressured into like, okay, if the uncertainty element is too big, then it can affect how we, to incorporate it into some actionable science and decision making. So maybe that's driving it, but I think this is important, that wherever we can talk about likelihood, we should, and also clear some concepts. So RCP 8.5 is used and was described as a business as usual scenario. And this specific paper came by Hausfather and Peters, and many other papers came after that, but challenging that 8.5 is not business as usual, and is strongly assigned. In fact, our current policies are shown by these trajectories in yellow and red. And so anything that is closer to these trajectories should be more considered as a business as usual scenarios rather than these extreme case scenarios. So the point I want to make is that there's an increasing effort to assign likelihoods to these scenarios now. And the way you choose to do your study can be based on that. So you can choose to work with RCP 4.5 or 6.0, or more recently, the SSPs. So RCPs have turned into SSPs, and more you'll be hearing SSPs and working with SSPs. Essentially the same thing. Those numbers are equivalent in terms of the effect of a particular emission scenario. And I'm happy to talk about it more later on if there are questions about SSPs and RCPs. So the point is likelihood of being assigned, and that probably should help. I'll see. I'll be interested to see if there are any comments about these comments to you. But let me move on to the other component of the uncertainty, that differences across climate models. And so, we have over 20 climate modeling centers out there. They come up with their best models, and the community for the last several decades have been, assembling all these model output and sharing it with the practitioners or scientists to just, make sense of future climate change. And so that's the CMIP effort. And so we had the CMIP 5 collection, the CMIP 3 before that, and now CMIP 6. So, when we analyze these models, we do see differences across these models in terms of how much specifically the warming is happening at a global or a regional scale. And I'll show that the global scale warming really correlates very strongly with the regional scale warming. So one of the most important metric that scientists look for in the model, in any global climate model, is what is the climate sensitivity of the model, which is like, for a particular emission, how much does it warm? And so this idea of equilibrium climate sensitivity has been long, ECS, and that's basically a simple idea, like if you double the CO2 from pre-industrial time, how much will the global mean temperature change? And so that's kind of a measure of climate sensitivity. And I'll share these slides. I've already done actually. So you can look at some of these links, and especially this reading here, if you're interested in like kind of the history of in thinking about climate sensitivity. Jewel Charney wrote this report in 1979, and where he kind of assigned, he talked to basically two scientists, well known at the time, Jim Hansen and Suki Manabe Suki Manabe was at GFDL, NOAA GFDL, and Jim Hansen was at NASA. And he asked them, what is the climate sensitivity? What do you think? Manabe said, I think 2. Jim Hansen said 4. He added, he kind of basically averaged it, said it's 3 and it plus 1.5. And that's where this 1.5 to 4.5 came in his report in 1979. And it stuck for a very long time. And at that time in 1979, they didn't have many, they barely had a 3-dimensional global climate model to work with. But our sense that the climate sensitivity was in this range has been very long, and like just shows how far scientific intuition and all can go. And in all these sophisticated modeling efforts showed that kind of these variation exist. And again, these exist across models. And Suki was working with a different model, and Hansen was working with a different model, and they were giving different things. And so the structure of model does give differences, although we tried to put our best understanding of the physics, So anyways, not belaboring this thing, the sensitivity is the big piece that drives the differences across models. And we're finding in CMIP6 that actually, if anything, it has increased, that we have several of these models very high sensitivity. And then, of course, this is a headache now how to deal with them. And you might have seen papers is saying, hey, these very hot models should not be considered for decision making. They're coming out of wrong reasons. So just a statement from IPCC, recent report in IPCC on this climate sensitivity, and it's and I was a little surprised by that they made a very strong statement, and I'll just read the last sentence here, which says that the AR6 assessed best estimate of the sensitivity to be 3 degrees Celsius, what Charney said, with a likely range of 2.5 to 4 C. So Charney's range was 1.5 to 4.5. That stuck for a very long time. And so this time the IPCC folks just reduced it even further. And that was really surprising. They have been more willing to keep it larger than smaller. As I said earlier, the regional climate change really correlates very well with these climate sensitivity. So if you're selecting models, it would be good to select across this climate sensitivity range. And when you do that, when you select a very hot model and a less hot model of a region, you are actually selecting across that range. So very quickly on this third component of uncertainty, and that comes from what we call this term climate variability. And it really is the fluctuations in our climate system. So without the benefit of climate change, we have had fluctuations in our historical climate. And I could show you some very short-term fluctuation that we call the El Nino Southern Oscillation that affects our climate, especially in the West, quite a bit. And right now we're in La Nina cycle that, and 2 years of persistent La Nina that's bringing this kind of pretty severe drought situation into the Southwest. So these fluctuations can happen on very short to very long time scales. And in our context of looking at climate, it's really the decadal scale fluctuation are important. So if a decadal scale fluctuation for some reason is taking us in a wetter or a drier situation, then it will affect what projections we are seeing in a particular model. So when a model is giving you a trajectory into the future, it also is seeing these decadal scale effects. So again, largely driven by stochasticity, and how much climate change is influencing climate variability is a question. Somewhere it's actually, most of the time it's difficult to answer it, and we're just trying to develop our understanding into that question. But climate variability also is tied to the experience of extreme weather. And that's one connection that we should always see, that it's not about change between two periods, but also it really matters to look at these time series, a sequence of climate across a time period, and within that, how the extremes are manifesting. And that's largely driven by the stochasticity in the climate system. So here I want to combine all three sources of uncertainty and just talk about for temperature and precipitation, how they manifest through the century, or how should we kind of think about them when we are thinking about where the uncertainty is coming from at a specific time horizon into the future. And what this is showing is the relative contribution, if you're starting from a point here, and then you're looking at the future, the relative contribution of these different components of sources of uncertainty. And so what I want to say for temperature, and that's again, all looking at regional, that in the short term for the next 10 years or so, the climate variability plays a big role. But beyond that, and throughout much of the 21st century, is the differences across the models that plays a big role. But after 2050, as I said earlier, the differences across emission scenarios become important. However, when you look at precipitation, it's a very different picture. As I said earlier, the role of emission scenario is very limited. Again, it's like how much precipitation you get. And largely, it's the difference across models and the climate variability that plays the largest role. And I would argue that climate variability plays a larger role than depicted here. So I would almost give 50-50 to blue and orange throughout the 21st century as a kind of rule of thumb. So how do we work with these uncertainties? And I guess you folks are probably quite familiar with some of this way of doing things, that we are working with specific climate scenarios. So we select a few scenarios and look at responses in our system in those scenarios. So that's one way to work across this uncertainty. And we have been really kind of encouraging practitioners to work across the uncertainty rather than work with kind of mean of all models, kind of climate change into the future. And there's limited things you can do when you just take the mean of everything. You cannot work with the time series data, for example, and look at fluctuation and sequence of climate, which you can do quite well when you kind of work with these scenarios. So yeah, so we have a spread, and you work across these scenarios. And what the philosophy I have, and I kind of promote, is there's no perfect way of doing this. Most of the time, just go by your hunch. There is some guidance here, but yes, working across this uncertainty. So in this case, this was work I did with the Nature Conservancy. They wanted to select 4 scenarios. They wanted to consider a hot dry, a hot wet, somewhere in the middle, and it's something like really a kind of the best case scenario, this warm wet future. So that's been kind of one of the approaches, and we have been developing tools, and the community has been developing tools to kind of that for practitioners to kind of visualize this bivariate scatter plot, working with very different kind of. I'm just showing temperature and today, but really you can work with all kinds of variables and make that choice of climate scenarios. So that's been one of the steps that has really advanced in the last few years, is the understanding that we should work with scenarios to incorporate the uncertainty spread, and then how do we, and these tools, how to select these scenarios. And so many of these tools have really appeared in the last 2 to 3 years. Folks have been also doing extra work in terms of picking models. So there's this whole effort to rank models. Maybe some of you are aware of this work by Linda Joyce and her team at the Forest Service. And they kind of made some model selection for regions and the whole country based on some of these rankings. So they did, and these rankings were done based on models, how good they were in kind of simulating historical climate. But I'll just say this, that it's better to be more inclusive than exclusive of models. Just because a model is doing well in the historic period doesn't mean that it'll also do better in the future. But if you're looking, I've known folks who have been studying projections in Alaska, and Jeremy Littell is one of my colleagues, and he did his own filtering of models. He just wanted to make sure that a model is getting the snow processes right. If it's not, then a lot is missing there. So you can use different filters to select models. But again, this idea is it's okay to be more inclusive, and actually that's recommended for most of the time. Okay, at this point, I just want to stop it and just ask Scott. Scott, I mean, I don't know, how much time do we have? I see just 10 minutes are remaining. I'm totally happy to stop here and have a discussion if folks have to go right at 2, but I'm happy to stay a little longer if.
I'm around. Are others still able to hang on? Thumbs up from Jimmy. Others? Jeff? Roughly, not to pin you down, but how much to run through the rest of the?
Oh, I have 5 minutes more, but maybe it's a good idea if you take some questions at this point, some discussion, and I'll probably get back to a few other things that I wanted to say about. I'm just getting more into now the issue with, we have covered, I think we have really nailed down in a pretty robust way how to work with climate. There's still a lot of work to be done in terms of how to get data and relevant data that you need. Sometimes that's not easily available, and working on that. But this whole piece about then how to connect climate change with ecological response, and that's where I think when I heard RAD and when I, all of that thing, how do we go from climate change to doing something like RAD? But those were some points I wanted to make in the next few slides, but I can do that later.
I do think that's one of the big questions that we've all been wrestling with, is exactly that. How do you go from that from that to the responses that you need? So that does set us up for a really good discussion. But Ben, I notice you and Daniel, you have to head out at the top of the hour. So I want to give you guys first chance to, if you have questions or comments, to pipe up and let us hear.
Well, I kind of had that. Well, since you were talking about the amount of models, let me back up a little bit. Since you were talking about the amount of models and the variability within the models, how do you decide how many models you're going to use when we are doing our assessments? Because the more inclusive you are, the more noise you'll lose than when you kind of stick to just a few, if I'm mistaken.
Yeah, that's a good question, and thanks for asking. So what I'm and maybe I'll go to the to my plot just to make that point clear. So when I'm making a choice, something like this, where I'm selecting 4 scenarios out of these 72 plausible futures, I would say I'm pretty inclusive. If I'm not selecting this model here and selecting another one for a specific reason, then there is an additional filter I'm adding. So by the most inclusive would be, I don't care about model ranking and all, I just choose these based on where they lie in this and the spread. That's more inclusive. That's what I meant by being more inclusive. So you can still select 3 future scenarios to work with and be very inclusive because you select it across the whole spread. You know, and there are different ways of it. You don't have to work with a single model. You can work with, you can say I'll work with 4 different spaces in this projection, a hot wet space where I'll take 5 of these models and average them and 5 from here, or, you know, and that's another way to go about assessing, you know, climate change or quantifying climate change. So yeah, I hope, does that help?
Absolutely. And then I was also wondering on a second note, because it seems like you weren't choosing the most extreme models from that. So why wouldn't we want to choose the most extreme?
Yeah, that's a great point. You know, and you know, so it's just and I would consider within, you know, most of the expression of future climate in that quadrant to have very similar attributes. So that's the thing, you know, when people try to get too optimal about it, which is, so part of the reason is that I'm, in that case, I may have brought a secondary filter to say, okay, these models are doing good for, are ranked highly for these several other reasons. I'm picking this versus this. So I may have made that choice in that case, added a secondary filter, but yeah, there's no specific reason not to pick the most extreme. I could have done that, and people do that at times, but also not to think that the most extreme model would be hugely different from one next to it. So they are very, very similar. And we're just looking at 2 variables. If you look at seasonally, they may shift. If you look at, if you instead precipitation, you do soil moisture, it may shift a little bit. So yeah, so just this idea of just finding the most extreme and picking that, yeah, is probably not what we recommend. Just pick from that space and don't think too much about it.
Understood. Thank you.
Ben, before Jimmy, did you have any questions? I know we just have a couple more minutes. Oh, Jimmy, floor is yours.
Ben just took his mic, turned his mic on, I think.
Oh, sorry.
Yeah, I was just wondering, to look at some of these models, do you need like specialized software of some kind to like view the results for some of these? I mean, you listed a lot of different models there in the last slide that you presented with the model ranking. And I was kind of just really briefly looking into some of them, and it seems like maybe there is some like extra steps needed to access results for some of them. And I was wondering like what maybe that would entail for, like, generally speaking, to access results from these models.
And results in terms of, you want to compare to historical data to see how good they're doing, right?
Yeah.
So yeah, so the best thing is to work with, when you want to do that kind of assessment, is work with the original GCM data, not the downscale data set. And just kind of see if, you know, what is the bias in terms of temperature, precip, etc. And so, for some variables like temperature and precip, it's very easy to find tools to give that to you, those data sets very quickly. The Climate Explorer tool is pretty good. That can sometimes get you very quickly to the data that's developed by the USGCRP. There's also this tool, let me share my screen quickly, that I use quite a bit. It's called the, well, I'll just write it in the chat. It's the Dutch folks have developed that a while ago. And it's also a Climate Explorer. That was the original Climate Explorer. And they have just, it's very quick to get these GCM data downloaded and even plotted and all of that. So yeah, I'll recommend that.
Awesome. Thank you.
Okay, Jimmy.
Yeah, thank you. Just an observation on all of these models and just how complex this situation is that we're in. The Woodwell Climate Research Center recently concluded that based upon their research, I think it's 86% of the models used in the IPCC report exclude permafrost thaw from their results. And I mean, I know roughly, I think it's like twice the carbon that's in the atmosphere is in permafrost, and we know that permafrost is thawing. So, I mean, just that figure alone makes me really skeptical of any trajectories that we see. So I don't know if you have any observations about how permafrost, our knowledge, our lack of knowledge about permafrost could play into these scenarios. Thank you.
Yeah, no, thanks for that question. And I'm assuming you're mostly talking about the permafrost response to the net carbon in the atmosphere, because there'll be a big source of carbon and carbon dioxide, and it's, and you just hope that some of these uncertainty from something like a permafrost, but also the source of carbon from permafrost gets into these carbon emission scenarios like the RCP 4.5, 6.0. And that's maybe one reason why we should consider some of these, maybe pinning down ourselves too closely to 4.5 is not a good risk assessment. We need to consider a wild card like, a 7.0 scenario, that could happen because we're not considering things like permafrost and other sources of carbon, especially 30 years down the road, if not. But yeah, but in terms of local climate change, it would be less of an issue. But also, yeah, then you can ask like how much, then the process of like these Earth system models, increasingly we are calling the GCMs, the ESMs, the Earth system models, are trying to really bring in the biological feedback very strongly and the land surface processes more strongly. So you hope that they're trying to get it, those processes in them, but I really don't know. I'll definitely ask around.
Yeah, thanks.
Jeff, go ahead.
Yeah, I'm just wondering, thanks Imtiaz for this presentation. It's mind blowing. I'm wondering, when we think about climate change results and their predictions, and then thinking about how they're applied to the landscape, I guess I struggle to think that the results are going to be the same across the globe. Say, for example, the desert Southwest and the Pacific Northwest. I don't see, and this is, my ignorance, but I don't see this the results being equally applied to a desert ecosystem or a desert zone, the same as a very, an opposite of a very cool and wet zone. So what efforts or what is happening out there in the climate change world to sort of address these landscape zone differences and expectations or outcomes of climate change?
Yeah, thank you, Jeff. I think it's a complex question, and it's just it cannot be addressed totally by the climate community, because we need to do the bring in the climate thing and then use more ecological impacts models to kind of give us a better sense of what the response would be. So in terms of most of these climate models are able to represent large scale features of a biome. So something like Northern Great Plains versus the Southwest, they're pretty remarkably well represented on a large scale. So in terms of the aridity of the land and kind of the basic vegetational response. So we are to that extent, the climate it will experience in terms of temperature, precipitation, even something like soil moisture, is adequately simulated across these diverse landscapes. But I think the big question is, what does that climate change mean for the ecological response in that region? And that could play out very differently between the Southwest, and there you cannot bring general rules. And that's really where you need to work with nuances of how, because the ecology is so complex in itself, the climate and the interaction between them is that's where we bring the word of complexity. Like, it's tremendous complexity here, and we need to be a little more nuanced as we look at these and really question the tools we are using, and what does a robust assessment look like? Are quantitative tools enough? And I have my personal sense is we should use them, we should develop models, but then we should bring in expertise on that subject matter to think beyond the quantitative approaches, really kind of think out of the box, because the models are really our constructs and they are limited in many ways. So I think we need to look for, when we're looking at so much complexity, that really bring in a participatory approach along with quantitative modeling. I hope I'm getting somewhere with that, answering that question, Jeff.
No, you really did. I mean, I was thinking kind of about that same thing. And Scott, maybe for the fellows, I mean, I think this is sort of an important discussion. They're going to have to be those ecosystem experts to bring to bear that science in climate change conversation. So good luck, fellows. We got your back, though.
That's important.
Yeah, that's right. So, and that's a really good point too that you bring up too, is matching up. And I'm thinking back to some of what Daniel was saying earlier, is making sure that we've got the models matched to those ecosystems and that provide the best performance in those cases. But at the same time, I don't know, maybe it's wrong to say hedging our bets by being a little bit more inclusive. Is that a right way of saying it? Imtiaz is expanding your host models instead of just kind of putting all your eggs in one basket.
Yes. And maybe I'll just go back to my couple slides left just to make that point. Maybe it will become clear through those graphics, and they were not put by me, but by other experts I know. So I think this whole point of doing it robustly, in our paper, we basically just talk about that, when you are planning an impact assessment, for a long time, ecologists and climate folks need to talk to each other in terms of selecting scenarios, understanding processes, understanding, what climate variables are important, and what is an appropriate ecological model, response model, etc., to use, whether it's a niche model or it's a bioclimatic envelope model or something else. And so that discussion has to happen between the two communities. And this is where the nuance comes in. This is where a good understanding of the system comes in. And then you kind of maybe go ahead and generate a quantitative information on the response of a system under different scenarios. But there's a step beyond that where you then need to bring in the experts and to see, are these quantitative response making sense? Should we hedge our bet? Well, should we really think about other surprises that could happen on the landscape based on what we know experientially and from our deep understanding of the system, which we cannot put in these models sometimes. The other thing I wanted to mention, and this paper, again, by my colleague, Shelley Crosby, this makes this very interesting point that, we have maybe, as I said earlier, we kind of figured out a way to work with climate uncertainty. But as you select a scenario, for example, you select a warm, wet scenario, based on the next steps of looking at ecological response under that scenario, you may find that actually there's not a single future, ecological future for that scenario. You can have multiple futures that could result from that single scenario. And that's critical, because that's where we are saying that, hey, there is enough uncertainty in the ecological responses as well. There's uncertainty in the climate change, but that even if we work with these scenarios, we should be open to what different ecological futures could come out of that. And that's critical, I think, and this is my last slide actually, when we are looking at something like a decision-making framework like RED, and this is an example in their paper as well. We're looking at this red spruce forest system in Acadia National Park. Thinking about what the future could look like, and it could, and in terms of decision making, like they could resist, they could accept a more shrub-like system, or they could direct it to a temperate forest. And again, all of that has to come from this kind of knowledge that you just cannot go and make these decisions. A strong scientific basis has to happen from here, that you can recognize that, hey, maybe there is a future for red spruce under some of these scenarios. There's a future for, if you don't do anything, there's a future going into shrub, and then there's a future for this temperate forest that perhaps we can take the system to. And again, these decisions will be made and revisited at different times. So you can make a certain decision or criteria to make that decision for next 5 years, but it can change. And so, yes, all of this is a moving target for us. So I think that it helped me answer, go to these slides.
I like that, the one slide, especially where you've got the ecological processes tied with the modeling. I'm going to have to pull that paper. I have not read that.
Oh, okay. Yeah. Let me know if you can find it.
So open it up to more questions, comments. Dina, Gabriel, Josh. Gabriel, go ahead.
So I was going to say that last slide with the uncertainty of ecological futures, I think was really, really useful to think about. I think we've been talking a lot about climate uncertainty, but that is a really big factor on like the management that we decide to do. And it's just, I've been thinking of like what decisions we can make here. And a lot of those decisions are tied to, yeah, what possible like ecological futures we're going to have. Like, are we going to have, for example, here, we're going to have a future where forests are even, I mean, forests are already the natural occurring ecosystem here, but we do have grasslands, managed grasslands, but are they going to be even more successful, or grassland is going to be even harder to maintain? You know, is that going to be the near future? And are we going to have to stop doing things now? Or is it going to be like there's uncertainty or not? So regarding that, you made me think a lot about when to make those decisions of when to give up on a landscape or when to, you know, direct towards a ideal scenario. And I know we are considering, you know, we want to consider giving recommendations regarding monitoring. So what are your thoughts on like having a monitoring plan that looks at those thresholds, like those points where you are likely to diverge between future ecological scenarios? I don't know if I'm making myself clear, but it's like those points where like a decision should be made on whether to change your management, I guess. I feel like that's something
yeah,
that
that's
we
a
really
great
want to get at.
question.
Yeah.
I did share that paper which talks about developing these ecological scenarios to support something like RAD. But you know, I think it's one of the problems we have in terms of why we are having difficulty connecting climate to ecological responses is that we don't have robust ecological data. And so when you talk about monitoring, that would actually, everything else in terms of helping us determine where the trajectory is going for an ecosystem or a habitat, it also gives us this data to kind of maybe do more with, you know, in terms of improving our science and understanding of processes. So I think the more and more of working with observations, remote sensing or in situ monitoring is going to be critical, just to help us just evaluate our own decisions of the past and just, you know, and seeing where it's going. Because, you know, it's not that we made a wrong decision in the past if the trajectory goes a different way because something else played out. You know, you had a volcanic eruption, or you went into a different climate variability mode for 10 years and it's all dry or it's too wet. And so it's just so important to plan for that variability.
Other questions, comments? Josh, you're quiet. Any questions from you?
No, this was great. I'm still kind of pondering all the implications, but
I know.
yeah, I learned a lot.
Yeah, and if you don't have my email, you can get it from Scott or Nightford, and if you have questions, I'm always available to chat.
Well, and if there's no other questions, then I will shut it all down and give everybody back their time. And I appreciate it. Thank you very much. This has been very enlightening, Imtiaz. I really appreciate it. This is, I was just getting those papers downloaded. I was going to share them all again. The Shelley's paper, I don't know if the CCC fellows remember it. I had posted that one earlier, but that's a good reminder. It had those figures, Gabriel, that you thought were really enlightening. So that's I'll pass that around again, make sure everybody has a chance to read that, because I think we're kind of to that point to where everything's kind of starting to click. A lot of that information that we've been collecting, we've been collating, been running vulnerability assessments, talking about those. How do all these pieces of the puzzle fit together? And that's a good summary paper for that discussion. So.
Yeah, I've been telling NIFR you guys are ahead of the curve in terms of the way you're looking at this. That's not been my experience with other engagement with Fish and Wildlife Service. So, it's really great to see.
Excellent. Well, I sure appreciate it. Thanks, everybody. I think I'm going to end on a high note.
Thank you. Great to meet you all. And good luck.
Take care
to the fellows.
And, I'll pass along the email contacts and papers and stuff here directly.
Great. Thanks.
All right. Thanks
Yeah.
again,
Thank
everybody.
you.
Take care.